Visible light. The Hubble Space Telescope, launched in 1990 above Earth's atmosphere, sees the universe the way human eyes would if they were perfect and never tired. Without atmospheric blur, Hubble resolved individual stars in distant galaxies, measured the expansion rate of the universe, and photographed objects 14 billion light-years away. Its images, the pillars of creation, the ultra-deep field, colliding galaxies, became the defining pictures of modern astronomy. Visible light reaches Earth naturally, but turbulence in the atmosphere smears it. Hubble moved above that smear. Infrared. The James Webb Space Telescope sees heat. Every object warmer than absolute zero emits infrared radiation, and Webb's mirrors, gold-coated, cooled to minus 233 degrees Celsius, detect it with unprecedented precision. Infrared penetrates dust clouds that block visible light entirely, revealing star-forming regions, exoplanet atmospheres, and galaxies from less than 300 million years after the Big Bang. Where Hubble saw the early universe dimly, Webb sees it in detail. Webb also detects the chemical fingerprints of molecules, water, carbon dioxide, methane, in the atmospheres of planets orbiting other stars. Ultraviolet. Galax and the ultraviolet instruments aboard Hubble observe wavelengths shorter than visible light, the wavelengths produced by young, massive, hot stars that burn through their fuel in millions of years rather than billions. Ultraviolet observations map where star formation is actively occurring across galaxies, trace the web of hydrogen gas between them, and reveal the outer atmospheres of stars invisible at other wavelengths. Earth's atmosphere absorbs ultraviolet radiation completely. Every ultraviolet image of the sky required a telescope in orbit. X-ray. The Chandra X-ray Observatory and XMM Newton detect photons with up to 1,000 times the energy of visible light. These wavelengths are produced only at extreme temperatures, millions of degrees, which means they come exclusively from the most violent environments in the universe, the superheated gas around black holes, the shock waves expanding from supernova remnants, and the vast plasma clouds filling galaxy clusters. Chandra's observations of the Bullet cluster confirmed that the visible mass of colliding galaxy clusters cannot account for their gravitational behavior, providing some of the strongest direct evidence for dark matter. Gamma ray. The Fermi Gamma Ray Space Telescope detects the most energetic photons in the electromagnetic spectrum, produced in collisions between particles moving near the speed of light. Fermi scans the entire sky every 3 hours. It has cataloged pulsars, detected gamma-ray bursts, the brightest explosions in the observable universe, and mapped 2 enormous structures called the Fermi bubbles, lobes extending 25,000 light-years above and below the galactic center whose origin remains unexplained. Fermi also searches for signatures of dark matter annihilation in the gamma-ray background. None has been confirmed. Microwave. The Planck Space Telescope and its predecessor WMAP measured the cosmic microwave background, the thermal afterglow of the Big Bang, now cooled to 2.725 degrees above absolute zero and filling all of space uniformly. The temperature variations in this radiation, fluctuations of roughly 1 part in 100,000, encode the initial conditions of the universe. From them, Planck determined the age of the universe to be 13.8 billion years, measured the proportions of ordinary matter, and dark energy, and mapped the seeds that would eventually collapse into every galaxy and galaxy cluster that exists today. Gravitational wave. LIGO and Virgo are not telescopes in the electromagnetic sense. They detect ripples in spacetime caused by the acceleration of massive objects. When 2 black holes merge, the distortion in spacetime propagates outward at the speed of light. LIGO detects it as a change in the length of its 4-kilometer arms, smaller than 1/10,000th the diameter of a proton. Since the first confirmed detection in 2015, dozens of black hole and neutron star mergers have been observed. The planned LISA mission will extend this to space, 3 spacecraft separated by millions of kilometers, sensitive to lower frequency waves from supermassive black hole mergers, and potentially from the first moments after the Big Bang. Thanks for watching. Do you think we'll ever figure out what dark matter actually is? Let us know in the comments down below. Also, please remember to like and subscribe if you enjoyed.